morning.
I'm Cindy Kelly, Atomic Heritage Foundation, here in Santa Fe, New Mexico. It is Saturday, February 4, 2017, and I have with me Jay Shelton. My first question is to please say your name, full name, and spell it.
Jay Shelton, Jayshgelton.
Perfect. Now, Jay, why don't you just tell us a little bit about yourself and what you've been doing for the last umpteen years?
Well, I've always been interested in science. I've always been interested in teaching from the very beginning of my life. So I went to college with an eye towards probably becoming a teacher, majored in chemistry and physics because that was a broad. I thought that was broad. I'm interested in the physical sciences more than life sciences. I went to graduate school, got a PhD in physics, and then got a teaching job. I was a professor of physics at Williams College for 6 years and got interested in wood stoves and fireplaces, and then for the next 12 or 15 years, I owned and operated wood stove and fireplace testing and research laboratory, part of it in the east, part of it here. And then I wanted to get back to teaching, so then in the next 25 years or so, I've been a high school math and science teacher, mostly physics and chemistry and calculus, but a little bit of everything.
Terrific. As I was explaining, we're doing a program on Los Alamos innovations, the innovations of the Manhattan Project. It's a very broad topic. Why don't you begin with one of your favorite angles on this, or talk about the Manhattan Project and why it has been seen as a crucible of innovation.
Well, my perspective maybe is a little different. I've been a high school science teacher in New Mexico, and I'm very interested in content which is clearly relevant to the kids. And the Manhattan Project and disposal of nuclear waste has been really big and really of interest to the kids and their parents. So I focused a lot of my teaching on nuclear issues because of where I live.
So let's go back. Pretend that I'm in the 9th grade, sitting in your class. Can you tell me about radiation? Can you tell me what is nuclear? What's going on at Los Alamos that I should know about, or how did this all come about? What was the Manhattan Project trying to do?
That was a lot of questions.
It was. Choose what you would like to answer.
I mean, in terms of radiation, which was where you started and where I start with my students, because most of the public does not fully understand all the kinds of radiation. I have the kids come up with any word that they associate with radiation randomly for about 15 minutes, and I put the words on the board in 3 columns. And then we later talk about why I did that. And the distinction is radiation which is capable of ionizing atoms, radiation which is not, and radiation can under some circumstances. And then we talk about the health effects, because that's primarily what the kids are potentially afraid of, or society is. Non-ionizing radiation can have health effects, but they're pretty modest and hard to measure. Ionizing radiation clearly does have health effects because it ionizes atoms and molecules, which means it kicks electrons out, which means that it disrupts bonds, because bonds between atoms to make molecules are all about what the electrons are doing. So it can change the chemistry, it can change the chemicals in your body, and therefore of course there's a potential health impact. So that's the primary distinction, whether or not the energy is high enough to knock electrons out and hence change the chemistry. The kinds of radiation, of course, which do that are X-rays and gamma rays and any fast particle with mass.
So where does gamma, what radioactive elements produce gamma rays?
Radioactivity can produce gamma radiation and beta and alpha and neutrons. There's a variety of interesting stuff. There are many radioactive atoms that are naturally on Earth. There are some radioactive atoms which you can produce with nuclear reactions, as reactors and bombs do. Am I answering your question?
Yeah, sure. Whatever you would, however you think it'd be most edifying to people to better understand what alpha, beta, and gamma radiation is about?
Alpha elephant, beta bunny, gamma Sammy sidewinder. My kids all look at me when I say that and think the guy's lost his marbles. What's going on? But there was, I've done a lot of work with groups of teachers. Some of it sponsored and helped by Los Alamos, some of it not, to try to develop tools that help people understand. And that was a phrase that we came up with: alpha elephant, beta bunny, gamma Sammy sidewinder. Alpha particles are like elephants in the sense that they are by far the heaviest of those three, if you look at the mass. And they also are the slowest. Beta bunny and an alpha particle is a nucleus of a helium-4 atom, 2 protons and 2 neutrons. That's pretty massive in this context. Beta radiation is 1 electron going fast. Way, way, way less massive by factors of thousands. And they go faster. And then gamma Sammy sidewinder is gamma radiation, which has no rest mass, travels at light speed. You can't go any faster. And so that's a way to help the kids understand or remember some distinctions amongst them all.
I've never heard that. That's excellent.
I had a student draw, who was a very good artist, draw alpha and beta and a gamma and make them look like those three creatures. And they're very different in what they do too. Alpha radiation is slow, has a very hard time getting through other atoms, and therefore doesn't really penetrate our body coming at it from the outside. Beta is in between. It's an electron. It's a little smaller, and it can maybe go a few millimeters into our bodies coming from the outside. Gamma radiation is very penetrating and can go completely through you, and sometimes it goes completely through you and does nothing to you because it went through. It didn't deposit any of its energy. Some of it does get deposited. So they're very different in terms of what they do and what kinds of protective measurements are necessary if you've got stuff in the environment which is emitting that. Alpha radiation coming at you from the outside, no worry. And there is alpha radiation and beta and gamma coming from everything. Everything is naturally radioactive. Alpha is a concern if you eat or breathe materials which are going to send out that radiation, because then you don't have a protective layer of dead skin. Beta radiation also is mostly a concern when consumed or breathed. Gamma is a concern anywhere because it does penetrate.
So tell us more.
Well, I guess the next issue is how dangerous are these things? And the health concern is primarily cancer. There are other things that ionizing radiation can do, but I think the biggest concern is cancer. It results when any one of these kinds of radiation scrambles the chemistry of DNA in a very particular way, and it doesn't get repaired, which it usually does. And it can lead to cells having the wrong instructions. The cells are now told, "Ooh, I love myself, I am going to make more of me." And that just proceeds and proceeds and proceeds, and you get a tumor. How much radiation does it take to be a significant risk? I think the only way to address that is by comparison. So here are the two reference points that I think are perhaps most useful. One is, since there is natural background radiation everywhere, it's coming down from the cosmos, it's coming from our own bodies, which have carbon-14 and potassium-40, totally natural. Other things in us, comes from the air, from radon, comes from the ground. So it's all around us at low levels. The dose that we get, let's say, I'll back up a moment. One of the ways, if you want to scare somebody, what you do is you tell them that we get hit either internally or externally by ionizing radiation on the order of 10 or 15,000 times every second. That's the rate at which we are being bombarded. And each one of those has enough energy to perhaps on average ionize thousands, tens of thousands of atoms in your body, molecules in your body. So if you add up the total number of busted bonds that we get, it's something on the order of 1 billion. Depends a lot on details, but roughly speaking, we might get 1 billion broken chemicals in our body every second of our entire lives. And if you don't get quantitative about that, you just sort of get scared and think, my God, I must be dead. Well, we're not. And so the question is, well, why not? And I love to ask students that. And usually at the 9th grade level, where I've done a lot of teaching, some of them will realize that actually the number of molecules in our body is big. And although billion is big, maybe it's tiny compared to what's there. And that is part of the answer. Part of the answer is that a lot of the damage is totally inconsequential. Part of the answer is that a lot of the damage that could be gets repaired. So the bottom line is it's not really that scary. So in order to help people understand how dangerous various kinds of radiation are, various sources, the 2 points of comparison that I think are most useful are, one is, what is the daily the probability of getting cancer from the daily natural radiation dose that we get. And I'm not going to give a number for the probability of getting cancer, but there's a certain risk of getting cancer from a daily dose. The unit that Los Alamos has always used, and it's one of the few institutions in the world, I don't know if they still use it, but it's not the metric system, it's the rem and the millirem. So in terms of millirems, the average dose per person per day in the US is on the order of 1 millirem. The average dose from one dental or extremity x-ray diagnostic procedure is on the order of 1 millirem. So apparently millirem is not too scary. We get it every day naturally, and we get it every time we have a diagnostic procedure. So probably that's pretty negligible. So in terms of millirems, how many do you need to get in order to have a detectable chance, increased chance of getting cancer? And it's on the order of 10 or 20,000 millirems. Gives you roughly a 1% increase chance of getting cancer sometime in your lifetime. Below that, it's unmeasurable. There may be an effect, there may not, but it's on the order of tens of thousands to have a chance. So now we can look at various things that people are afraid of. Radon in your house, getting an extra x-ray. There are some people in Santa Fe that I know who never get x-rays because they're scared to death they're going to get cancer. Well, if the x-ray is a millirem, I guess here's another number that we could toss out. The number of millirems we naturally get in a lifetime is 20 or 30,000 millirems. So getting one medically useful diagnostic x-ray might be a good balance in terms of healthcare as opposed to additional risk. And the risk is unmeasurable at that level. There are a few medical procedures which can have measurable consequences. And again, in medicine, it's always a trade-off. What's the benefit of having this procedure? One of the most interesting experiences we had in our classroom was a mother of a child who I had in 9th grade who called up and said, may I come by your classroom right after I get out of the hospital, and would you check the radiation dose that I'm emitting and give me your opinion as to whether or not it is safe for me to go home and hug my children? Interesting request, and of course I said yes. She had had a therapeutic iodine treatment of an overactive thyroid. And the half-life of that isotope is a few days. I forget exactly the number. And so you stay isolated for a while. You live in a motel. And after a while, it's considered okay to go home. So she came in. And I didn't tell the kids all that was going on. I believe in mysteries and puzzles. So they all had Geiger counters. So she walks in and they turn them on, and everybody's Geiger counter is going way higher than it used to be without extra sources in the room. And so I asked them to explore and try to, I told the mother in advance what I wanted to do with this educationally. So they explored around, and they ultimately located that it was she, and she was brave enough to let them find out where in her body most of it was. And it was everywhere, but of course it's more at the thyroid. And she was an absolute screamer in terms of Geiger counters making an exciting noise. Normally you get, one count every 2 seconds in our background classroom. So it was screaming. And so then we talked about, okay, now what's the dose going to be? The Geiger counter has a little conversion factor for counts per second to millirems per hour or whatever. And I don't remember exactly what the numbers were, but of course it was negligible. And of course it's okay to go home and hug your children. She also had her clothing. because you have this radioactive iodine everywhere in your body to some extent. So it's in your clothing and whatever. And it was just a very educational experience. Looks scary, but you look at the numbers, and hugging a child with some fraction of a milligram, if you hug them for hours a day, it was negligible. I'm a great believer in being quantitative. You have to be quantitative. If you're just scared of radiation, life's no fun. How much? And how much does it take to be a problem? And then you can decide how to react. I think that's very important for ninth graders, very important for everybody in our society, and very important with every hazard, not just ionizing radiation. Ionizing radiation happens to be one where quantification of health impacts has been very well researched. There are some others where there's less that's known. So it is possible to quantify risk. I also had a student who still lives in Santa Fe. She's a firefighter and a paramedic. And one of her claims to fame was that early on in her high school career, she was a volunteer in local fire departments, and they have ways for kids to volunteer in a useful way. She was so anxious to become a real volunteer, not sort of relegated to non-dangerous things, that she actually got, through hard work and lobbying, the state rules on how old you have to be become a paramedic or a firefighter. She got them changed by a year or two. So she's famous in my experience. There's a procedure where you inject radioactive atoms, and where you have a bone that is damaged but not cracked enough to show up in an X-ray, there is biochemical activity there, and you can inject a compound which preferentially goes where bone is working on repairing itself, and then you look at the image that you get from the radiation coming from the person, and you can see whether there's damage which X-rays don't pick up. I'm sorry, I don't remember the name of the isotope right now. And I said, can I come? And so we went down to the hospital here in town. I brought instruments. She knew about the instruments. We asked the technician whether it was okay if I stand there while we do it, and went through the whole procedure of opening up the lead container and pulling out the thing and giving it to her, and then looking how it spreads, and then they do their imaging of her. It's wonderful to have a student who is so unafraid and understanding, because she understands radiation, that it's just totally a non-issue to have the procedure done and to have your science teacher there to get some data that we can then talk to the class about. It was a lot of fun. The other thing that I can recall that we did that's more related to LANL is to do with WIPP. We were very involved with, as a school, as a class, and I as a person, with the whole development of whether or not the WIPP site ought to be there, etc. It was very, very controversial, all kinds of public hearings. I testified. My class and I did all kinds of research on it. And after it opened, we were able as a school, we have annual field trips, and we took the entire ninth grade class down to the WIPP site, underground, and even when there was waste underground, to where the waste was until 9/11, and then things sort of got tightened up, and we did it once after that. They gave us special permission. But here's the interesting story. Of course, there are going to be some families, some parents who think that taking children to the WIPP site when waste is there is unreasonably dangerous and refuse to let their children go. And as a school, we of course will respect that, and we say that's fine. So what I did, I'm always looking for the most educational value in these things. We had lots of radiation detection instruments, and the kids who stayed had instruments, the kids who went had instruments, and we took them everywhere, measured everything. Enough so that everybody could calculate approximately what their total dose was from radiation from any source during the whole trip. Well, I knew, and it was so interesting for the kids to discover that if you went on the trip, you got a smaller, I shouldn't say much, but you got a smaller radiation dose, always trivial from background radiation. And understanding why it was smaller when you go to this radioactive waste dump was so interesting. The waste is stored, first of all, Carlsbad is lower in elevation, so there's more air between you and the cosmic radiation, and so there's less cosmic background radiation. The soil has less uranium and thorium in it naturally, and therefore there's less ground radiation, natural background radiation. So you benefit from that in any case. But when you go down into the salt caverns, this is 2,000 or 3,000 feet thick of salt, and the radiation, I mean, the waste is somewhere in the middle. The salt is very clean radiologically. It has very little uranium, much less uranium and potassium and well, particularly uranium and thorium, than soil and dirt does. So the background radiation dose is close to zero. With our little Geiger counters, which get 30 counts a minute in our classroom in Santa Fe, we got maybe 1 or 2 counts a minute. You just turn it on and you listen and you look at it and nothing happens. Very rarely you hear a tick. So you have all this time that you're at lower elevation, lower uranium background. You have all this time when you're down in the tunnels, a few hours, where you get virtually no background radiation. And then you go up to the waste, and when you get with them, they don't let us get very close to the waste, but we were, 100 feet away. You could see the barrels there, which was very exciting for the kids, and you could see the Geiger counters registering a little bit more. And then you add all that up, and of course, we got less radiation dose than the kids who stayed in Santa Fe. And I don't know, I think that children, at 9th grade, their minds can be changed. They can have fear of something and lose it, and I saw that as one of my jobs. Let's quantify risk. I'm not sure I influenced any parents, although I think I did. I think some of the parents thought, oh, they got more radiation dose here, and it sort of opens the window to, well, now wait a minute, does 1 atom of plutonium kill you, or 1 zap from alpha? No. So it was really wonderful educationally. We were not able to do it after a while, but it was a lot of fun. We also did a lot of work up around LANL itself, in Acid Canyon, collecting samples. There have been various degrees of cleanup in areas where waste was dumped very informally in the early days. And we always took kids up when there was some new development up there and collected samples and brought them back and made measurements, and it was fun. It was fun and very educational. Yeah, the Waste Isolation Pilot Plant, which abbreviates WIPP, WIPP, is a major national nuclear waste disposal site, which is now active in southern New Mexico near Carlsbad in salt deposits. It takes waste from related to come from national labs. I guess it's all related to military applications. Waste from making bombs, and it's low-level waste from making bombs. It's not spent fuel from nuclear reactors. It's the floor sweepings and the gloves and the booties and stuff that wasn't very concentrated is what goes down there. When the proposal was put forth to have that waste be in New Mexico, it of course was controversial. And if there's one issue or one kind of issue which gets me really worked up emotionally, it's when people are trying to make smart decisions about an area where there's technical information or science, and they have the wrong information that they're using to make a judgment. I have no problem with anybody saying, I don't want the waste dumped down there or whatever, as long as they understand what the risk is. So I spend a lot of my effort with my students and in my testimony trying to quantify, because that's my thing, you have to quantify how bad the risk is. And one of the issues which had people really, really scared was trucks carrying this radioactive waste, these WIPP trucks, traveling through Santa Fe. And initially they were going to go right down St. Francis Drive, a main road in Santa Fe. Ultimately, money was provided to build a bypass, so it went around Santa Fe. And of course now people are developing all the land around the bypass, because I don't think that really was the issue. I'm good friends with a lot of the anti-nuclear folks in Santa Fe, and our kids have even volunteered with them on the community service programs our school had. But one of the issues, that's one of the issues that drove me crazy, because we got a hold of various studies that had been done, and of course these issues are studied endlessly by all kinds of groups before a decision is made. The studies that we tended to focus on were the ones done by New Mexico group, not DOE, not LANL, but supposedly, and I think actually, an independent group of technically competent scientists that the state of New Mexico hired to say, how dangerous is this? And for the truck, I guess I'll give you a few details. They have various degrees of accidents. I guess this is done in any accident study, and they range from 0 to 10 or something, how bad the accident is. And a 0 or a 1 is a bumper toucher, and a 2 and a 3, and they get more and more violent. And at the extreme end, You have the truck exceeding the speed limit, hitting a gasoline truck exceeding the speed limit in a head-on collision, and the WIPP containers come apart and the drums break and there's a fire, and so radioactive material is carried up into the air, and therefore some people breathe it. You got to find a way to get it inside people to have it be really hazardous. Well, there was a newspaper article which, when that study came out, said WIPP trucks traveling through Santa Fe will kill 2 to 3 people from cancer, and went on and on and on. So I got the study, we looked at the study, and where does this number come from? And it's there. What they do for each degree of accident is say how many people are likely to die over the next century or two, taking into account the half-life and the extent the material lasts in the environment. And they also give a probability for each kind of accident. The probability for bumper touchers is moderately high, 1%, 5% or something for the trucks coming through Santa Fe. The probability for the one that has deaths, none of the others did, they were too small to even talk about, was 0.0000001%. I don't remember the number. And so yes, the study did say 2 to 3 people would die, but no, it's not likely. And they come up with the most likely number of fatalities due to the probabilities of all ranges of accidents, and it's a tiny, tiny fraction of 1. Negligible compared to every other decision you make in your life. As a, how many people die from other causes in Santa Fe? Huge. So I tried to persuade people that the risk of accidents and trucks coming through Santa Fe was utterly negligible, and it was very interesting. I got a lot of flack from other people who were testifying on the other side at the hearing, of course. And it was clear that there are people who really do believe that 1 atom of plutonium will kill you. And so my job during all these times was to try to say, no, it's more than 1. And in fact, you already have, I pointed out, 100,000 or tens of thousands of atoms in plutonium of your body. Everybody does, because it's been vaporized into the atmosphere and it's everywhere, and we get a little bit. And does it matter? No. What's the dose? Utterly negligible. Much less than any other decision you make in your life, like taking a vacation in the Rockies or flying to Europe or whatever.
Yes.
I'm looking for guidance from you for where to go.
No, this is good. I was just so. Have you looked at the Japanese epidemiological studies and the death rates or the incidence of excess cancers associated with various levels of exposure? I'm just curious. And it sounds like you may not have.
I don't feel like I'm an expert, but yes, I have looked at those some, and I've looked quite a bit more at Chernobyl and Fukushima with the same purpose I always have, and that is how bad. In terms of the World War II numbers, is that what you're talking about?
Yes. In terms of the survivors. And they've done all sorts of longevity studies.
Yeah, I'm not an expert on that, no.
But you did look at 3 Mile Island and Chernobyl, the risks associated with them?
Fukushima?
Well, especially Fukushima, because again, I try to do things in class that are current.
Sure.
And that was going on when I still had students. So, yeah, I did look at that, but it applies to all these other, well, especially the reactor accidents, not so much World War II. And the conclusion of all the good studies, the studies that are done by competent people, my understanding is the conclusion is that there is far greater risk to health from all the other things that are going on that are not radiological. The fear of the radiological health causes evacuations, and evacuations can be kind of panicky. Enormous psychological stress, I don't know what all the issues are. People are afraid to eat. I suppose they do eat, but there's all these ancillary things which have measurable consequences. Suicide rates, I think, in some cases are measurable. In Chernobyl's case, people have done some awful things, thinking that they had to do it to protect themselves. And it's due to all that misinformation about the dangers of radiation that is the biggest health risk in terms of consequences. for those ones, including in Japan. Now, the one thing that I do like is that apparently, perhaps related to Fukushima, but maybe it was going on already, that I think that the internationally recommended radiation dose levels at which you don't need to evacuate or you can bring people back in have gone way up compared to 10 years ago. And very logically, I mean, it used to be that people were being so conservative that they would keep people out for no reason at all. Now there's some local discretion, and it gets down to this level. That's the one place where I've seen a little bit of sensible quantification come into some of these issues. But it's the fear that causes the damage more than the radiation. Too bad. It really is. It's tragic. Unnecessary. Oh, and the fish. Oh, I had all kinds of people, including my son who lives on the West Coast. Oh, is it safe to eat the fish? Because I read an article that you can detect strontium-90 or something in the fish, and it came from the reactor accident in Japan, and can I eat the fish? And there have been some wonderful, good quantitative analyses of the fish and the radiation. And of course, because science is so good these days, you can find one atom almost of an element, and sure, yeah, there is strontium-90 in there. But what else is in there? And I don't remember all the comparisons, but of course the dose from the atoms that came from the reactor is way smaller than all the other doses that are natural that are in fish. You've got to be quantitative to understand whether or not to be worried. And if you are quantitative, then you can stop worrying and having all those bad psychological impacts about things that don't have any impact. You can worry about things that do matter, not things that don't. That helps you and it helps the world. Another thing I did and shared with my students was look at the standards. There was, every time there's a news report, I try to get down to the bottom of it. One of them was, oh, the spinach has been, or the lettuce or something, is now unsafe to eat in some of the areas near the reactor. And so I looked up what those standards are. What is the dose that you would get if you did eat it? And what are the assumptions that it's dangerous to eat it? And everything is fascinatingly conservative. The assumptions are, I'll remember a few of them, are that we're going to declare it dangerous if, now I don't remember what the dose is that you would get, but it's a few milligrams or 100 milligrams or something which has an unmeasurable effect. That's sort of the threshold, maybe 100, I don't know. But they also assume that that food is the only food you eat, whatever the contaminant is. So I'm only going to eat lettuce for the next year, and that you're going to eat it for a year, and and at the same level of contamination, and then we're going to calculate the dose to you. And there's some other conservative things in there. And so when you find out how the standards are set, well, no, I'm not going to worry about the fish. I'm not going to worry about the lettuce, because the assumptions are so conservative, but by many, many orders of magnitude. That's interesting, and it's quantitative. And it was really fun sharing that with my ninth graders. Oh. Maybe it's not so bad. All right. Here's an interesting little factor to do with measuring radiation. One of the things that teachers are fond of telling everybody, the public and their students, is that everything is radioactive, including you and me. And that when you sleep next to somebody, you gamma rays from your potassium-40, entirely natural, zap your partner or whatever. And so we talked about that quite a bit and tried to measure it. Now it's hard to measure, and it's hard to measure because the background radiation environment that we live in is so strong. And so over all the years I was teaching, we've found 2 environments where you can actually measure the radioactivity coming off of a normal adult healthy body or a kid. One was at the WIPP site, and when you go underground, the background radiation dose is so low that if you hold a very sensitive detector out by itself in the mines and get a reading, and then you get all the ninth graders to come around and squeeze and get as close as they can, so you got all these bodies around it, we had a very slight measurable uptick in the radiation dose. The other environment where we found that works is in water, in a swimming pool. I didn't have a chance to do this with my kids as much as I would like to, but again, if you have an underwater capable detector and you put it there without a body near it and then just one person come up and touch it, you get a very substantial increase in radiation. The problem is the background radiation is so high, and so in reality, if you hug somebody, you both get a smaller dose because each of you is blocking background radiation dose more than you're contributing your own shine. So it takes a very rare environment in a submarine or underwater or in a salt mine in order to have being close to somebody result in an increase in net dose. That was fun. How a Geiger counter works. I should have brought one. But a Geiger counter has inside of it a Geiger tube. And a Geiger counter only detects ionizing radiation. My students would often ask, what happens if I put it in a microwave oven? Well, if you put a Geiger counter in a microwave oven, you will kill it, because the electronics will get fried due to all kinds of other circumstances. But it only detects ionizing radiation, and you may recall or you may know that ionizing radiation knocks electrons off of atoms and molecules that it happens to encounter. So the detector has to be sensitive to that. So inside every Geiger counter there is one or more Geiger tubes. The ones in that little Geiger counters that most people have are not very big. They're about that long and maybe a centimeter or two thick. The tube has a wire going down the middle and a metal can around the outside and kind of a special mixture of gases, but that's not critical. So ionizing radiation comes along. It has to get through the metal, which means no alpha radiation will get in, but it's good for beta and especially for gamma. So the ionizing radiation comes through and it will ionize some of the gas that's in there. Now, I left out a really important thing. There is a huge voltage difference between the wire and the can, which means if there's any charge in the air, it'll get very strongly. The electrons get pulled down to the wire and the positive ions get pushed out to the can. It's a very, very strong electric field. So if you create a bunch of free electrons, which is what ionizing radiation does, it knocks them out, the electron gets pulled very strongly towards the central wire. Now the central wire electronics are not usually sensitive to detect a single electron. Now of course that ionizing radiation may ionize a few atoms, but here's the real key. You get amplification and you get a cascade. You get one electron which is now loose from its atom, can start moving very fast towards the wire. It gets going so fast that it itself becomes ionizing radiation, and when it bumps into another air molecule, it will knock an electron or two off of it. Now you have two, and they now get accelerated and they bump into another, and you get more and more. You get a cascade of electrons being created by this process, and crude, even though it's still a very small number of electrons, you can afford the electronics that can detect that pulse of electrons hitting the wire. That makes a tick if the electronics do that, makes a light blink, makes a counter go up by one. So it directly is detecting ions that are created by ionizing radiation, which of course is what we need. Oscilloscopes are awesome instruments. One of their claims to fame is that they can measure things that are happening very, very quickly in time. If you have a meter with a little needle on it, and the needle has to go back and forth, it's got mass, it's got inertia, and it takes a little while for it to respond, and your eye can't catch it. So an oscilloscope is a way to measure something where it is electrons only which are moving, and they are so lightweight that they can go up and down and whatever you want them to do very, very quickly, which allows you to see things that are happening over very, very short time periods. So an oscilloscope has an electron gun and it has a screen. You look at the screen and you can see glowing light up there, lines, whatever the system does. But the key is you have an electron gun, you have a vacuum between the gun and the screen. The screen is coated with a material which will glow when the electrons hit it. So that's how you're going to see where the beam of electrons is hitting. So you have to have a way to have the beam get very narrow, not a big spray, and there are ways of doing that. As the beam is traveling from the gun, and the way you make an electron gun is you just warm up a wire so it's red hot. Anything that's red hot has enough energy that it's throwing off electrons. And so any wire red hot, and you keep refeeding it electrons from a battery or from the power grid or whatever. So you have electrons that are being spewed off, and you get a beam that's going pretty fast towards the screen. As it goes towards the screen, it passes through between plates of metal, which may be connected to the thing you're trying to measure. If this plate gets to be a little negative and this one a little bit positive, and you have a negative electron in here, it's going to get pushed down by the negative plate and pulled down by the positive plate, and so it'll get deflected a little bit. You don't want it to get pulled and have a collision. You just want the beam direction to change a tad. So you can steer it up and down by the charge on these two plates, which can be connected to an experiment. Typically that's true. You have another pair of plates that are oriented like this, and typically that's sort of a time base. They are automatically and electronically charged, positive and negative, in a gradual way to make the beam go across the screen. And then if something's happening, it'll go up when this one does something. So it's a graph of what's happening in your experiment as a function of time. And because it's only electrons that go up and down and go this way, you can measure things that occur in a nanosecond. You can measure things, I don't know if that was true during the Manhattan Project, but it is the tool for looking at things that are occurring quickly. Well, let's see, the energy in anything that's fissioning, whether it be a bomb or a nuclear reactor or just a decay. Let's talk about uranium, since that's one of the common ways of doing it. The energy comes from the nucleus, and it comes because in a fission process, the nucleus fissions, which means it comes apart. And interestingly, the energy is not nuclear, it is electric. When the nucleus comes apart and gets just a tiny bit distant from the way it was packed together, both pieces, they aren't equal halves, but both pieces are highly charged electrically, because the nucleus of an atom contains protons and neutrons. Protons are positively charged, and they're really close to each other in a nucleus. The neutrons are neutral. So the existence of the protons means the nucleus is being pushed really hard apart, but there's a strong nuclear force which keeps it together as long as everything is close together. So as soon as you get a tiny bit of separation, you have this fierce repulsion due to the like charges, positive and positive, and that's where almost all the energy comes from. It's released in a nuclear bomb. It's electric energy. It really is electric energy, triggered by a nuclear process, kind of. So the whole atom consists of a nucleus and a bunch of electrons going around. And I think a very useful model for any atom is that if you were to blow it up, make a scale model of it, the size of a soccer field or a football field, and keep everything in scale. The nucleus is in the middle, 50-yard line, and if you walk out there, you can see it. You can't see it from the outside because it's on the order of a centimeter in the middle of the field. The electrons you can't see because they're too small, even when the atom is magnified that much. And in fact, electrons are so small that even today, nobody knows how small they are. People do experiments shooting electrons at each other and trying to get a bump, something other than just a gradual push. Can't do it, despite all the accelerators. So the electrons are invisible. There's this little lump in the middle, and that's what all atoms look like when magnified that much. That's relevant for how you get a chain reaction, a fission reaction going. So the energy comes from these two pieces being pushed apart. How do you get them to fall apart? Well, there's a spontaneous fission rate, which is very, very small. It's kind of like a radioactive decay. It doesn't do you any good because it's too unlikely. So you have to encourage it. And of course you want, in a bomb and a reactor, to get the fissioning to occur on your demand, not just randomly waiting. So it turns out that if you send a neutron, which is one of the particles that's already there in a nucleus, neutrons and protons, but if you send a neutron and it hits a nucleus, it has to be a pretty direct hit. That will often, with some nuclei, like the ones that are used in reactors and bombs, cause this fissioning to occur. Well, that's nice, you get a whole bunch of energy, but you need more than one. And so the way that most people have designed reactors, and certainly bombs, it takes advantage of the fact that when you do get a fission, not only do you get these two big parts that push away on each other, but you get a few neutrons to boot. Between 2 and 3 neutrons come out as well. Well, since it took a neutron to make this guy fission, maybe we can use those neutrons to make another guy fission, and we can get a whole bunch of them to go. That is really hard, and here's why. That model of the atom, almost all empty space. I mean, really, you stand and look at it, and you can't even see the nucleus when you're at the goalpost, and that's an atom. It's almost nothing. So if you get one atom to fission, and you get 2 or 3 neutrons to come out, they go out in straight lines in random directions. You can't control where they go. So suppose we have a few other atoms around this one. Let's make a pile of 6 or 8 football field size things around there. So 2 or 3 neutrons come off, and they go in a straight line. What are the odds that you're going to hit a nucleus of one of those other atoms that's around you. It's nil, because they are so small and you're going in random directions. So the folks at LANL had to figure out how many atoms you need and in what geometry to make it probable that one or two, that more than one anyway, of each of those new neutrons that are created are going to stimulate another fission, because you want to get a whole bunch of them to occur at one time. And that's where you come up with masses that are about this big, as I understand it, for fissional material, for uranium or plutonium. It's a little different. In order to have a reasonable chance that you're going to be able to use the neutrons that come from some fissions to create new, so you get a chain reaction. I did bring, but I don't think I'll use it. But a really nice example of a chain reaction is to light one end of a book of matches. If you light it over here, this one's going to burn too. What fire needs in order to spread is you have to get it hot enough to ignite it to make it go. Well, when this one goes, it does get hot enough to heat up this one. It gets hot enough to heat up that one, and it spreads. In the case of a nuclear reaction, it's not the heat, not the temperature, but it's the neutrons which spread and bump into another one. So it is extremely hard. The probability solo of hitting another atom that you just have a whole bunch of them, and it doesn't do to spread them out in a sheet or anything else, because then most of them are going to miss. You need to make it as compact a shape as you can, which is spherical. And so that's what they figured out and did.
So maybe you can now talk about aspects of the design of the bomb that...
Okay. Yeah, so all right, there's some other problems. So you need to have a big enough mass, which is maybe grapefruit sized or whatever. And then if you can get a fission to start, maybe you'll get a bomb. Well, the answer is you don't. You can build that and you can get a fission to start and you'll get a bunch of other than a fission, but these reactions release so much energy so quickly that if you were able to suddenly create a critical mass, which is what this is called, it would disassemble itself before a significant number of the atoms had fissioned. And the reason is that the atoms, the mass, whatever, get so hot, so fast, that the pressure builds up so much from the vapor that it just pushes the uranium or the plutonium apart, and you get a mess, but you don't get a big bang. You have to somehow try to keep it there despite the fact that it's getting unbelievably hot for as long as you can, so that more of the atoms will have a chance to fission, so the total energy release is big enough to make a big bomb. So as I understand it, they worked on two ways of doing that. The simpler way was to have two pieces of uranium that were not right next to each other, because you don't want this reaction to start. And then you try to bring them together in a way which will hold them together for as long as you can. And the design was to have a gun, and I guess they had a core at one end and a hollow piece at the other end, both made out of uranium, enriched uranium. And you set off an ordinary explosive down here to shoot one piece as fast as you possibly can down the tube, and it will slip over the cylinder at the other end, and pretty soon it gets critical and things start happening. But because of the inertia of bringing this slug in, that it will be around for enough time to get some small fraction of the atoms to fission so that you get a bomb. The efficiency, as I understand, was pretty low. Almost all the atoms got vaporized and the energy was not released. But it worked. And so it was using inertia, I guess, really to hold them together long enough to have those neutrons find other atoms before all the atoms get vaporized and just go away. The other design, which I think was the one that Los Alamos really struggled at and weren't even sure they could achieve it. This gun thing they thought would probably work, not very efficient. Involved taking plutonium, I think is what they used, and compressing it. Again, I guess it's inertial in the same sense, but instead of having a hollow target or a solid target and a hollow tube and bring them together, you try to compress everything spherically, symmetrically to bring the critical mass together. That is really hard engineering problem. The energy released is so fierce in here. If you don't have equal pressure coming in from all sides and every square millimeter of all sides, if there's one place where the pressure is a little bit less when you're trying to squeeze this thing, then all the material is going to squeak out the little hole. Conventional explosives were used to compress this stuff, just like conventional explosives were used to shoot in this gun design. But the task of having uniform pressure from a spherical explosive, I understand, was really hard. I think it took years just to see if they could do that. Part of it, of course, is timing. You have to have each part of the explosive go off at the same time. But it's also the manufacturing of the explosive has to be unrealistically uniform. You can't have 0.01% higher explosive power here than here, because then it's going to squirt out over here before it's held in long enough to get enough reaction to be worthwhile. Hard engineering.
That's great. That gives you a real good sense of why this was challenging.
Yeah.
Yeah. Very. I mean, one thing you might talk about is the state of electronics. For example, you say you need these detonations at exactly the same millisecond. And
yeah, I know a little about that. So when we set off this huge distributed explosive, and you need all parts of it to go at the same time, you have to worry about everything. You have to worry about the time that it takes electrical signals. There are a bunch of detonators that are involved, I presume. I'm not really an expert. But you have a whole bunch of electrical signals that are coming to set it off. And they have to arrive at exactly the same time. And so, of course, you worry about the length of the cable. Electrical signals go through conductors at light speed, or 20% of light speed. It's very, very fast. And if you have an extra foot of cable going to this igniter compared to that one, it costs you a nanosecond. And I think that's probably a killer. You can't do that. And then when you want a little spark to go off, either to initiate those signals, I don't know what was happening down here in the explosive, but anytime you want to initiate something, if you want it to happen reliably, I know a little about this because I collect some of these things. There were a lot of electronic tubes that had radioactive material in them. There was a spark gap, and there are two places with a little gap in between, and a spark is going to go across, and it's going to go across on command of something else in the circuit. And you don't want any hesitation or delay. And so you coat one of these, or both of these electrodes, with radioactive material to ionize the air between these two things, so that when you get a big surge of electrons that needs to jump across that gap, they won't have to wait unreliably for the lightning stroke or the spark or whatever to get things started. It's continuously there. This idea was, I think, sort of fraudulently used in spark plugs in the late 40s and 50s. People thought, oh, we want the spark plugs in our cars and trucks to go off reliably, so you could buy polonium-coated spark plugs. I think it was mostly a sales gimmick. But there's a real principle there. You want ionized air around gaps where you want a reliable transmission of a signal.
They were very clever indeed.
Ever since I came to New Mexico, which was like 35 years ago, but particularly when I started teaching, which was 25 years ago, as a teacher, I am probably the craziest teacher that I've ever known about having things to demonstrate and show. I never go to any class, including math classes, and it can be completely irrelevant. I try to make it relevant, but if you don't have the interest of your audience, you don't get anywhere. So it was a real natural that I started collecting nuclear stuff, and the theme of my collection has always been things that illustrate changing public attitudes towards radiation and radioactivity. And there's been a complete swing starting in 1895 or so. Up until 1930, everybody thought that the more you breathed and drank, the healthier you were, and the more quicker you'd get cured from almost any ailment. All false, but that was the belief. And the reason that was the belief is that people, once radioactivity was discovered, they then discovered that a lot of the traditional health springs and spas, which had been in use for centuries, if not millennia, were a little bit radioactive. Stuff coming out of the ground, radon dissolved, and stuff dissolved in water. It made sense. So they presumed that the reason people got so healthy going to the springs, which I think was not really documented, must be because of the radioactivity, and therefore if we could supply radioactivity to people's homes in the way of drinking water, breathing, whatever, it would be a great seller, and it was. It was a huge business for decades, 1910, 20, 30. So there were a lot of devices that were made back then which intentionally, the most common device was called a Revigator. It was a jug which was lined with radium ore, and you fill it with water. Radium decays into radon. Radon is a gas, so it can emerge out of the walls into the water, dissolved in the water, and then you drink the water, and it does everything for you. The personal testimonials were outstandingly impressive, as personal testimonials always are. So there was a lot of stuff like that, pro-health radiation and radioactivity. Then around 1930, the public began to wise up. I think the scientists and the engineers, long before that, realized that there's a limit to if there's any benefit at all. It was used to treat cancer, too, way back then. They gave high doses of radiation to cancer tumors way back in the early days. But then the pendulum swung, and we're now in an era where I think some people believe that single atom plutonium is fatal. And so I've just got all kinds of stuff representing that. After World War II, atomic and nuclear was very positively perceived. So people made salt shakers in the shape of fat man and little boy. You know, they're just little things, all kinds of stuff. They made jewelry out of uranium ore that people were very proud to wear, all kinds of stuff. It helped sell your product if you said the word radioactive and nuclear and atomic. So I collected a lot of that kind of stuff. Those are the two main things. And then, of course, recently it's been very anti, and I've got a lot of buttons, anti-nuclear buttons that say all kinds of cute things. But the stuff that's most interesting is the pro-health stuff from the early days, and then the euphoria over anything nuclear after World War II.
So since you've tracked this, when did the pendulum swing the other way? Where people... I mean, even in the 40s, people were promoting health spas and radiation doses. It was maybe the 50s or 60s. It's interesting. I collect all this stuff, but I'm not really interested in tracking exactly when things shifted and why. When I talk to other teachers at the school where I taught about why the pervasive feeling is so anti-nuclear now, the answer that I got that made sense to me was it's the mushroom cloud imagery from World War II. It can be very destructive. Radiation, of course, is incredibly helpful in health and all kinds of engineering things now, but it can be destructive. And for some reason, that image is more stuck in people's brains than the other possible images. I'm not sure. The anti-nuclear folks in Santa Fe that I worked with a lot, I would try to get quantitative about risk. I'd try to talk about these accidents of the trucks going through town. And finally, I would get some of them to admit that, well, I suppose that's true, that the likelihood of an accident which would cause serious harm is really close to zero. So then I asked, well, then why are you, if you accept that, why are you still so against anything nuclear? And I think I got an honest answer. It's because they're against nuclear war and nuclear weapons. And anything they can do to impede or just be against things nuclear, they hope will make it less likely that there'll be nuclear war. Now, I don't logically see the connection between disposal of radioactive waste at WIPP and encouraging nuclear war, but they did. You know, if you can dispose of the waste, then you can build more bombs. I don't think they're connected, but they did. So I kind of understood their point of view. That's interesting. What was the other part of your question?
Well, I guess that was the collections, and do you have a couple favorites in your collection that you want to talk about, or what were there any artifacts that your students especially enjoyed seeing or using?
Well, the most dramatic for my purpose of illustrating changes in public attitudes was some of these Revigators, these clay crocks that made water radioactive, had decals on them. which I can almost quote from memory. Again, I'm interested in changing public attitudes, and the details would say this Revigator will make the water as radioactive as the most healthful springs of the world. And that says a lot about public attitudes at that time. I mean, that's why I loved these devices. We love this stuff. It's really, really good. So those were fun to show to the kids. Kids like things that are dramatic, and of course I have uranium ore. I have some beautiful, large, colorful pieces of intensely radioactive ore. And that's exciting for the kids to see. We, of course, had a large cloud chamber. And the kids would say, well, what should we put in it to make the track so we can see where all this ionization that radiation makes? And it quickly became apparent that we didn't need to put anything in it, that background radiation is so healthy that we don't put anything in it now. You just set it all up, put the dry ice under it, get it all cold, and look in there, and pew, pew, pew. You see tracks all over the place, and they loved seeing that and trying to deflect the tracks with magnets and doing other little things that you'd think might have an impact. That was very exciting for the students. That's not historically significant, but it's educationally impactful.
Let's see.
Oh, cosmetics. The French were into pushing radioactivity in cosmetics. Thorium, radium, but they called it Thoradia was the name of the brand, which may still exist today, I'm not sure. But they actually made face powders which had radioactive materials in them. And they had ads, a beautiful ad of a lady being illuminated, her face being illuminated from below, very dramatic. The same faces occurred in ads for many things over the centuries, over the decades. But the radiance that you get from using radioactive cosmetics was interesting. Has nothing to do with it, but it worked to sell the product. This was back in those days when it sold the product to say it was radioactive. Ointments, salves, toothpastes were all made with radioactive materials. Not significant, but measurable. Those were fun things in my collection. Oh, yeah, ointments, radioactive ointments. Cures you faster, was the claim.
That's great.
Do you think any of those items at the time were hazardous for people to use? Or, I mean, you hear the story of the radium dial girls some of whom got cancer, or the ointments were too bad and the radon.
Okay, were some of them actually hazardous? One certainly was. It was called Radithor. And I have dozens and dozens of bottles because that was so important in public attitude towards radiation. I have a huge collection of the bottles, empty. It was a solution not of radon gas in water. Radon gas has a half-life of 2 or 3 days, and so after, as a collector, you're never going to find any left. It had radium dissolved in water. And again, people thought that the more you do this stuff, the better off you are in terms of health. And there was a very wealthy man whose name I don't recall, who in 1929, 30, 31 promoted this product. He may have been, maybe he was the man behind it, but he certainly told his friends about it. It was very expensive, like I think $1 a bottle, which in 1930 was huge. He drank a bottle every day. He'd give it away to his friends. And he died 2 or 3 years after he started doing this, because if you load your body up with radium, you are in bad shape. It stays in your body because it chemically kind of looks like something your body might need. And when he died, that is a marking point in a sense historically. And he was famous, and this product was famous. The public, I think, certainly had a chance to wake up and think, oh, maybe this can be overdone. That's a very interesting product. Oh, and there was so much radium in these bottles. I shouldn't say so much. It doesn't take very many atoms to be exciting. But one reason collectors love them is that the bottles that have not been rinsed out, you can measure the radioactive residue. And if the cork is still with the bottle, the cork is loaded because, of course, the material soaked into the cork. The liquid's dried out. And so from a collecting point of view, a bottle with a cork and a label gets a premium price. It's still hot and will be for another few millennia, since the half-life is 15 or 1600 years for radium. So fun for a long time.
All right,
Do you have to store any of your artifacts specially, or?
Good question. Storage. And it goes back to alpha, beta, gamma radiation and what they do. Any product that I have that sends out primarily alpha and beta, they're almost all pretty small. I don't worry about it, because alpha particles can only travel through no more than an inch of air, and there's none of the energy left. Beta particles can go through maybe a few feet of air, but you have it on a shelf and you never get any dose to you from alpha and beta radiation from these things. Gamma radiation you can, and so some of my stronger sources like the uranium ore, I don't store in rooms where I spend much time, but that's about all I do. Here's the one thing I do worry about, and perhaps I haven't done my quantitative homework even enough, but things that emit a lot of radon gas, then I'm going to breathe it, and then it's going to be inside my body. And as I said before, internal materials that are radioactive are much more hazardous than external materials. So things that emit a lot of radon gas and things that are particularly intense, like the ores, I keep in a shed outside the house. And I have really enjoyed taking some of my students to the hospital in Los Alamos. This was quite a while ago, where they have the facility, which is the best at that time anyway, for detecting how much plutonium do you have in your lungs or in your body. You know about those rooms? There's also one down near the WIPP site. The game is again to have a room with no background radiation, because the radiations from plutonium are mostly alpha, which won't get out of your body and won't get through the air, so you can't detect it. And then there's a little bit of fairly weak gamma or X-ray radiation. So that's what you have to look at. Low probability, low energy, hard to see. So you need to have as little radiation coming, natural radiation coming from all around. And the way hospitals have done that, I suppose it could have been done underwater, but I don't know of any underwater facility. And so what they do is build a room which has walls, floor, ceiling, door made out of 4 or 6 inch thick steel. Mass is what helps more than anything else. Doesn't matter too much what the material is. So they use 6 inch thick or 4 inch thick panels. And here's the thing that's really interesting. It has to be old steel, because all steel and all products, all materials in our world have contamination from atmospheric weapons testing. And so if you want really low background, you can't just buy lead or buy steel, because it has a very small number of atoms in it. So what they did is to find steel that was manufactured and refined, etc., before there was any atmospheric testing, which means before 1940 or 41 or whatever, or 40, whatever the date is. What was the date of Trinity?
45.
45, excuse me, of course, I knew that. And so what they do is generally find old battleships, which have steel plates that are like this, and cut them up, make them into rooms and doors. The hinges on these things, I mean, it was such fun for the kids. They've got to be really well lubricated, of course. And the inertia is just phenomenal, but it is possible. You got to be careful not to pull for too long, because then it's going to keep going. But we were able to put one of our students, they asked for a volunteer, and one of our students went inside. So that's the first thing, keep away background radiation. The patient lies down on a bed, and then there are a whole bunch of the most sensitive detectors for low energy gamma rays that are arrayed all around the person, the body. And you have to be in there for quite a long time to accumulate. And these devices can measure the energy of each gamma ray and only look at the ones which they know come from plutonium. There are all kinds. And that's the way you do it in these really fancy, and it's a weird room. They bring all these tubes down close to you. They don't touch you, but they're looking for the gammas coming from you. So one of our kids did it. Of course, they found new plutonium. They found potassium, because we're all full of natural radioactive potassium that puts out a low energy gamma ray. So the girl was alive, but not contaminated, our student who was in there.
Oh, that's great. You wonder if an older person had been the subject, as opposed to a very young person, an older person who lived through all the atmospheric testing, whether there'd be more plutonium.
I would be quite certain it's undetectable.
It would be.
I mean, I'm not an expert on that,
just
but
curious.
I think you need to actually be Well, no, I don't know the numbers.
Okay.
But I doubt it very much.
Yeah.
Because we're talking about, well, here's one reason why. The amount of plutonium in the environment and in our bodies has been going down, both because we take less in and we flush some of it out. The number I recall is a body burden of on the order of 100,000. And I think it's less than that now, but the average body burden for Americans. The half-life of plutonium is about 24 or 25,000 years, I think. So if you've got 100,000 atoms in you, you're going to get maybe 4 decays a year. So if you hop into that room and lie there for an hour, nothing is going to happen. No plutonium is going to send out its gamma ray to be detected. So I think that's the answer. You have to have way, way more than we accumulate from our environment to have any chance of detecting it. And of course, any chance to have any health effect. Yeah, there are some interesting applications of radioactivity in the environment. Carbon-14 dating, which can be associated with tree rings, but carbon-14 dating doesn't work for anything that's only 50 or 60 or 70 years old because of the substantial change in atmospheric carbon-14 caused by atmospheric weapons testing. It still is fine for older stuff if it hasn't been contaminated. It depends how carefully, but carbon-14 dating has to be done a lot more carefully now because we've added so much carbon-14 that is not the natural steady produced rate from cosmic rays hitting the upper atmosphere. Tritium also exists naturally in our environment at a fairly low level, but large amounts of it are created and released in atmospheric weapons testing. I think tritium has been used for discovering fraudulently dated wine. Wine has got a lot of water. Water is H2O. It's got a lot of hydrogen. Therefore, if there are any isotopes of hydrogen like tritium and deuterium, they'll be there. And so if you look at the tritium content of a wine that claims to be 70 years old or 100 years old, it should be whatever the natural concentration was back then before we changed it with atmospheric testing. And I suspect that there have been some wines that have been fraudulently promoted, and that's a very clever way to reveal that, to detect it.
Just in case you've talked about this with your students, you know how hospitals take great care if there's a radioactive material to dispose it appropriately. But a lot of the diagnostic tests that inject radioactive material in people, it gets disposed the natural way.
Yeah.
So, yeah.
Oh, I know a whole lot about that.
Okay, good.
Because that was another one of our big projects.
Oh, perfect.
There have been a bunch of them. One project which we could also talk about, I'll mention first, was people in Santa Fe being worried they were being contaminated by the emissions, air emissions from Los Alamos. And what isotopes might we be able to detect? And we did a whole project around that. But here's another one. There was a newspaper article. That's how these things usually started for me. For decades, there was a laundry in Santa Fe which laundered radioactive contaminated clothing from lanolin power plants and research labs or whatever on Sinai Road. And it was there for decades. I knew about it decades before it became a public issue, and so did a lot of other science teachers. We thought, well, that's interesting. But suddenly it jumped out. And of course, people not being quantitative got worried about it. So where's this radioactive material going? Well, it's going down the drain. Well, where does it go? Well, it goes down to the waste processing plant down on Airport Road in Santa Fe. Oh, well then where does the water go? Well, it gets used to water polo fields and soccer fields. Oh my goodness, my children are playing soccer on plutonium-contaminated grass. And it was a huge deal, of course. And I and my students were sort of observing this and speculating about it. And it took me more than a day to think, we can yell and scream about this forever. Somebody ought to measure how much is down there. I mean, the mechanism is there. Of course, there are going to be atoms down there. So we launched that project, and it was a huge project for a couple of years for us. So Among other things, we went down to the fields and sampled the soil and brought it back and measured it. The state actually got involved towards the end because they were scared too. Everybody said, what's the state doing about this? So we would collect samples jointly with the state on these playing fields and mix up the sample and split it. This is a good scientific technique. They'd measure it for the things they wanted. We did some of the same. And so we could compare and see if we're getting agreement. We always did get agreement. They were able to do some things we couldn't. So we had split samples with the state. We collected samples, and then people started worrying about, well, maybe it's not just in the water, maybe it's in the sludge, which of course it would be. And so they take the sludge from the processing plant and dig it into some acres of fields. And it just sits there and decays and morphs or whatever. But there's these fields, which are not used for growing things, and people don't normally have access to them, that are very smelly. And that's where the sludge goes. We also took a tour of the processing plant, and we got direct samples of sludge and of water directly from the plant. They dipped down in and picked it up. It was very exciting for the students and me. So we analyzed all this stuff. Number one, we found a huge amount of radioactive iodine from the hospital. That was by far the most radioactive material. Iodine is a beautiful material for diagnostic work with thyroids and for therapeutic work with thyroids, and maybe other things too. And there's some other things that hospitals use which have short half-lives, and therefore I believe the general standard is you don't have to do anything. And of course, people who have iodine in their bodies excrete iodine, and that goes right down to the processing plant. So we saw iodine all over the place. It was the most exciting, easy to see radionuclide. But we looked for the others that should be coming from the laundry. We looked for uranium and plutonium, and I forget all the ones, cesium, strontium, things that might be related with nuclear reactors and with LANL. I think, as I recall, the only isotope that we saw that could have been associated with laundry was cobalt-60. And that was interesting because that is a waste product from fission reactions. And so the question is, well, how much is there and how do we figure out where it came from? And we did the obvious, and that is to take samples on the playing fields where the water is and take samples on the desert and the dirt around these playing fields where the water is not used and compare the cobalt-60, I think it was, content. And they were indistinguishable, a lot of noise in the data, but there wasn't more on the fields than there was any place in the environment. So it was related to, I think, atmospheric weapons testing again, very, very low levels. We had an upper limit on plutonium from, I think, the work that the state did. It can't be bigger than X or we would have seen it. So then we did calculations on health consequences. Suppose there is that much plutonium and cobalt, and suppose it is from the laundry. What does it do to you? And I don't remember the results, but of course it was utterly, utterly, utterly negligible. Anything you do, like traveling down to the soccer fields to play, is much more likely to kill you in a traffic accident than is the exposure to the materials that are there. So it was really, really clear result. I testified with those results when this issue was really hot. And this was one of the most educational moments for the students. Some people in town got really upset at me. And they wrote letters to the editor. They wrote a letter to the head of the school. There was an article in one of the newspapers claiming that I absolutely should be instantly fired. How can we possibly have somebody like this as a science teacher in Santa Fe? It just went on and on and on. It was very ugly. And I went to the head of the school. The kids, and again, this was really educational for the students. They had done the work with me, and we just measured it, we just reported, and this happens when you do good science? Well, sometimes it does. The head of the school said, particularly in response to the letter that was written to the school, that was just, fire him, he's a disaster. His suggestion with that and the newspaper stuff is don't do anything. It'll blow over, and trying to defend it or writing, I don't know. I think it was probably a good choice. It just blew over, and we treated it as an educational moment for the students. Look what happens. Isn't that interesting? I wonder why they think that. And so we made a big discussion out of it. That's how it ended, and ultimately laundry left town. Not for a few more years, I think. It just was politically hard. There were, in fact, there were all kinds of things, lawsuits and stuff, and it was not science-based, the consequences, but they're not there anymore. For a while, they had that as a way station where they collect laundry and then take it someplace else to wash it. But I don't think it's there at all now.
On a similar note, I've heard a lot of people claim, and we heard one in earlier interview, that they had seen various strange glows at Los Alamos. People at Taos were saying, I see a strange glow at Los Alamos. Other people in Santa Fe were sure, you know, that the water's coming down, the runoff from the Mesa is carrying toxins and, you know, radioactive material to Santa Fe. Not being a resident here, I haven't followed it all that closely, but could you, you know, with your...
I have not heard about the glows, but I am absolutely sure that any glows up there are due to street lights and fires and fireworks and whatever, not nuclear. In terms of contamination of water, yes, of course you can find plutonium atoms in the drainage, and you can find them everywhere, and I'm sure there are more in some of those drainages. The question is, how many are there? What is the potential health consequence? Again, we can measure single atoms these days, so the existence doesn't mean there's a problem. In my opinion, as a society, we need to assess the risk and decide whether the cost of cleaning that up is the biggest bang for the buck in terms of saving lives compared to other things. And what I think I have read about the water contamination is, yes, it's there. Actually, I'm not an expert on water contamination up there. I'm much more knowledgeable about air, because there were claimed worries in Santa Fe that air pollution. And so we had another big project where we collected soil samples, surface samples, all over Santa Fe and ultimately all over New Mexico and upwind as well as downwind, because we had to try to answer the questions. We got a list of the radionuclides that come out of the chimney that's associated with the linear reactor, which is where most of airborne stuff originates. We looked at all the annual reports and studies that Los Alamos does all the time about what the emissions are, so it was clear what was there. What might be detectable? We detected beryllium-7, which is one of the things that comes out the stack. I think I've got the isotope right. We got so excited that we actually might have finally measured something, because usually these experiments are all null. You don't find these things. But we did. We found beryllium-7. I talked to the head of the school, you know, how are we going to announce this? How are we going to handle, you know, revealing this information? Because it's going to be really sensitive for all kinds of people. So we did more measurements. And then at some point I called a scientist at LANL that I knew. LANL has been really helpful for northern New Mexico high school and probably elementary school teachers too, middle school teachers. And through various programs and that help, I knew some people up there. And I was talking to them, I don't know if I called him about this, but I mentioned that we had detected beryllium-7. And the idiot that I am, he said, well, you know, Jay, he was a perfect teacher. He didn't say, oh, I know what that is. He was a perfect teacher, and I try to be the same. He said, oh, very interesting. I think there's some beryllium-7 that's natural in the environment that comes from cosmic rays hitting the upper atmosphere. So you ought to look into that. That's all he said. He didn't say you're an idiot, Jay. So we looked into it, and that's why we went and collected samples upwind and downwind. We just tried to, all right, if it's from Los Alamos, there ought to be more of it downwind than other places, and went on and on. And it turns out, yes, we were seeing beryllium-7, and no, it was not any higher in concentration downwind from Los Alamos than any place else. We got samples actually internationally. Some of the kids went away on vacation and brought back little soil samples from I don't know where. They had fun. We had fun. They all have beryllium-7, and it's natural. So we did not detect pollution from LANL and Santa Fe from the air. We sure had fun trying, and we sure learned a lot. I wish science education were better in this nation for all kinds of reasons and critical thinking. I did what I could with the kids I had, but most people don't think critically and don't know enough science and don't try to be quantitative. One of the courses I taught last year after retiring was the value of being quantitative in any environmental or health issue. And it is so interesting to get numbers. There was an article about bacon will give you cancer. Study's been done that says you're going to get a 20% higher risk of getting colon cancer if you eat 2 slices of bacon a day. Well, of course, I decided this would be fun to look into. And the most important thing in health claims, if it's a 20% increase, a 20% increase over what background rate? And if you find out what the background rate was, and then you do all the numbers, it came out to be something like, if you've got 10,000 people who do or don't eat 2 slices of bacon every day for their lives, 9,000, I think maybe it's 999 of them will have no consequence at all. One of them might get colon cancer because of it. So you think about your life. Here I am. Do I deny myself the pleasure of bacon for the rest of my life? Or do I eat 2 slices every single day? Maybe I'll just do it once a week. Then I'll have 1 chance in 100,000 or 1,000,000. Is it worth it? Well, it might be. When you put numbers on it, you can make a logical decision rather than, oh, bacon, can't do it anymore. Well, no, that's not true. It's not true. How did we get on bacon?
Maybe this would be a good segue into talking about the importance of STEM education.
I really am grateful to Los Alamos for the help that they've given to all northern New Mexico people who want to avail themselves of it. I don't know whether the programs are still going on now. I hope they are. But the most life-changing program for me, they had a program where you could apply to spend 8 weeks in the summer working on a research project with a scientist. And that's my kind of project. I don't want to talk about teaching. I don't want to teach about teaching. I want to do science and then see if it applies. And it really was because of that I did that. And I worked in the environmental group, and my particular task was finding out whether it was plausible to use gamma ray spectroscopy instruments to detect what levels of plutonium in soil. So I did it. It was cool. I had all kinds of contaminated soil and did all kinds of measurements. But the main thing is that I got to know people, and people got to know me, and it opened up doors. Some of the instruments that we used in some of these projects I've described are very sophisticated instruments. And I was able to borrow from Los Alamos. They had, not all instruments are in use all the time. And it made actually all of these projects possible. The radon water and the contaminated soccer fields, all these things, the beryllium. I had to use instruments that high schools can't afford to have. But they had many, many programs for developing curriculum, nuclear curricula. I was involved with some of those for all ages between K and 12. Very active, very useful, very important in all of my nuclear activities. I couldn't have done it without the lab. Most present day health standards relating to radiation dose presume that there is a health consequence no matter how low the dose is. Now, as we talked about earlier, below something on the order of 10,000 millirems, it's unmeasurable. But maybe it's still there. Unmeasurable because there's so many cancers anyway that you can't see any increase from a dose that's small. But maybe there is an effect. And when you're looking at health consequences to large populations, if you've got 1 million people who've been exposed to 1 millirem, that's 1 million people millirems of radiation dose, and so there should be some cancers out there. If, in fact, there is an effect that's linear with dose, that it doesn't matter how small, it's still there. You can't measure effects due to radiation below whatever this number is, 10,000 millirems. And so that's not a fact. My understanding is that it's a regulatory policy, that since we don't know and we want to be conservative, we're going to do our calculations assuming that it's there. And that's a policy which you could discuss and change. You can't change science, but you can change that. Does that address all the issues you were asking
It's
about?
great, because the logical next question is, how clean is clean enough when you're thinking about cleaning up radioactive contaminated waste sites, for example?
Yeah, I think that's a bad policy to have, because when the doses are that low, if the effects are unmeasurable, they're negligible. Now, maybe that's not quite fair. I don't fully say that, but I almost feel that way. But the problem is the cost, that if you have a contaminated area after a reactor accident, or if somebody does a dirty bomb someplace or whatever, how are we going to decide how clean is clean enough and when people can move back in again? And the cost implication of assuming that the effect of the dose never drops to zero, but is always there, is gargantuan. So I think it's bad policy. We haven't had to face it very much. I mean, in Fukushima, they had to face it a little bit, and I think they've raised it a little bit and become a little more reasonable about when it's safe to move back again. But I think that in the future, that if we have some major event with very costly real estate, like a dirty bomb in a city, that people are going to, I hope that the society is going to wake up and realize, you know, it's fine for everybody who's there to get an extra 1,000 millirems every year. It's not going to result in a detectable impact. Or even if you assume that there is an impact at the low doses, how many people are going to die from cancer? And if you're going to be quantitative, yes, every life matters, but every life is not worth $100 billion. We need to sort of be a little bit quantitative about whether we spend it on preventing lives of one or two that we don't know are really there, or we spend it on hospitals and healthcare and things where we know there's an impact, or immunizations. It's just dumb and ineffective for societal health to spend gobs of money on something which is going to have a unmeasurable and at least negligible, if not zero, impact. I think it's terrible, and I hope it changes. I just will mention, because it's interesting, another complete topic that I discovered the other day where people are not being quantitative is the garbage patches in the Pacific Ocean. You see images, people talk about floating flotsam and all kinds of stuff, and you see these pictures of mountains of garbage. I did a lot of work on that last year in preparation for a course, and if you were to sail a ship through that, you would be lucky to see anything, is what I understand. In order to measure that there is plastic and garbage there, you have to troll. You put these nets behind the ship and you pick them up and you empty them and you keep doing that and you're measuring it. The average density is very, very low. Most of the pieces are invisibly small to the naked eye looking over the ship. All the pictures, occasionally you'll find a big fishing net. I mean, I'm not saying there's nothing out there that you can see. Occasionally you might find a plastic bag. The pictures that you see of mountains of this stuff are, I understand, all taken in bays and rivers and coastlines where it piles up. They're not pictures from out there. And it's all started with one person reporting in an exaggerated way what was there. Now, that doesn't mean it's not a problem necessarily. Little bits of plastic, I worry about them and stuff, but the visual imagery, which everybody has, is wrong, I believe, based upon what I tried to learn last year. It's hard to find research papers as opposed to advocacy papers in a lot of these areas.